Hello everyone, so today we'll be talking about acetone and methanol liquid are vaporized by a stream of gas of pure nitrogen and two through a 0.24 meter long Stefan tube. The vapor composition of the liquid vapor interface is 0.319 and 0.528 respectively for acetone and methanol. The total pressure is at 99.4 kilopascals and is maintained at 328.5 Kelvin throughout. The Stefan-Maxwell coefficients are 8.48, 13.72, and 19.91 millimeters squared per second, respectively. We're going to be solving for the evaporation of acetone and methanol. And later, we're going to be using Excel to try to find the using Euler's equation in Excel solver. So first, let's start off with our general equation and what kind of some of our momentum is here. So first, we will be doing is defining our driving force. So our driving force, we're going to denote that by dI. And then that dI is going to be actually to the change in dyi with respect to dz. Now, this is going to be equal to the summation of J with our molar component of yi times our molar flux of Nj minus our molar component of J times our molar flux of I. That's going to be all over the concentration. Then we have a dJ, which represents our Stefan-Maxwell coefficient. So this is our general equation that we have here, as again, our driving force is equal to our change in yi, which is our molar component of I, with respect to dz, which is equal to the summation of J of molar component yi times the molar flux of J minus the molar component of J times the molar flux of I divided by the Stefan-Maxwell coefficient times concentration. So now what if we were to assign I equals to 1, or for this case our acetone? What would this equation be? So we have our driving force of 1 denoted by 1, and then we have dy1 with respect to dz. That's equal to the summation of y1 that's going to be equal to this, which we have y1 n1 minus y1 n1 over c d11. And then we have plus y1 n2 minus y2 n1 over c d12. And then plus y1 n3 minus y3 n1 over c d13. Okay, so you do some simplification here. For this y1, n1, this is actually, if you notice this, these are same 2. So that's actually equal to 0. So this gets simplified just down to 0. And so for other ones, we have equal y1, n2 minus y2, n1. That's different. And this one is also different. So our simplification is we can completely wipe out that unit. So now we're going to introduce a new variable with the scaling factor to help us solve this. As what a scaling factor essentially does is it denotes everything from 0 to 1. So next to this, I'm going to put 0 to 1 to help us remember that. And what is the scaling factor equal to? The scaling factor is equal to the distance of z over the film thickness, which is represented by this delta. So this is our scaling factor. So now we can actually rearrange this to get the following. We can get First, we're going to turn this into a derivative, as we'll have d of the scaling factor is equal to dz divided by our film thickness. So now we can separate this from both sides and put the film thickness on the other side, where we get the following of the film thickness times our scaling factor is equal to dz. So now we can input this into our equation right here, where we have dy1. I'll write this in a different color, just so easily distinguishable. So we have dy1 over the scaling factor, because the scaling factor helps us solve for it later on. So that's very important for us to be able to use. And then we can actually put the scaling factor on the other side of our equation to where we get our scaling factor and then times, because again, it's in the denominator, so switching against the other side, we have y1 and 2 minus y2 and 1 over c d12 plus y1 and 3 minus y3 and 1 concentration times our Stefan-Maxwell coefficient. So now what we can do is we can actually separate and multiply out the scaling factor into all of our equations. Fix it down. So this allows us to do the following. So we have our first component, our scaling factor y1 and 2 over cd12 minus scaling factor y2 and 1. And then we have plus y1 and 3 scaling factor cd13, and then we have minus scaling factor y3 and 1 cd13. So next, what we have to do is we can do some more simplification here, and it's important that we kind of call out some important stuff right now. So in this, what's going on right here is we have this surface, and we actually have two things are increasing, our acetone or methanol, but our nitrogen is actually leaving. So that nitrogen, or our molar flux of nitrogen and 3, can actually just be 0. So this can be simplified, this can be eliminated, and then this can be further simplified. So another important thing to remember is that this dy1 equal to d0, 1. So with that in mind, we can do some further simplification here. y1 is equal to 1, with y2 is equal to 1, and then y3 also equal to 1 here. So we got to try to separate the molar flux to try to get us an equation out of that. d over our scaling factor. So what is this equal to? So if we remember, concentration is just simply P over RT. So this can be simplified into P D RT and our scaling factor. Or excuse me, our film thickness. Input our numbers here, our pressure is 10 to the 5 pascals. Our constant here is 10 to the negative 5. Remember, this is broad specifications. For R value, we'll put as 10. Our temperature, we'll put at 330. And our film thickness is 0.25. I know it says 2.4 up there, but it's just broad approximation. So what does this get us? Roughly 1/775. About. And that's not exact confirmation, but that's our approximation here. So now we're going to take it over to Excel. Hello everyone, so now we're going to be doing the Excel solver portion of this. I have my area right here. So just to define some terms real quick, what we're going to do is we're going to have our D112. So I do have it written back there for like what our values are, which were given to us. D112, D13, and D23. And that's going to be again equal to 8.48 e to the negative 6 as meters squared per second. Our D13 is equal to 13.72 e to the negative 6. And then D23 is 19.91 e to the negative 6. And again, that's all meters squared per second. For our P, R, T, and C values, for our pressure, we have, it was 99.4 kilopascals, but for this, we will be doing it in pascals, so we'll do 9.94 e to the 4th. Our R value, we have 8.314. And then for our temperature, we have 3.29 e to the 2 K value of not K value, of Kelvin. And then our concentration is 3.6.4. And then for our N1 and N2 values, we have N1 and N2. Our N1 and N2 is 0.001268. 0.001268. And then for our Z and DZ values, we have 2.4 e to the 1 and 2.4 e to the 4th. That's going to multiply by 1,000. So now we're going to first set up our counter. Well, actually, first I want to make this. Sorry, move this down a little bit. And create from selection. And then we got all those on the left side. Put this back up here. 0 and 1, 2. And should bring that all the way down. 1,000. Oops, not that far. So now we can begin our derivations here. We have our Z value, our Y1, Y2, and then Y3. So our Z value is just our counter times our DZ. Next time I put these as negative or as positives. There we go. So for our y1, if we remember what our y1 was from the problem, it was 0.0.319, 0.528. And our y3 is just going to be 1 minus, oops, 1 minus, there you go. There's our y1, y2, y3, and our z value. So now we're going to find our dy1 dz. This is going to be equal to y1 equal to y1 times n2 minus y2 times n1 divided by c times d12 plus negative y3 times n1 divided by c times d 13. So we get negative 1.24702. So now for our dy 2 dz, so our second derivative essentially, we will have y2 times n1 minus g2 times n2 divided by our concentration times d12 then plus our concentration times y3 and then it's not period, it's an underscore. Plus our y3 times n2 divided by concentration times d23. Now let's make this look all nice. We're gonna add in and so you guys gotta add in this negative. And I'll get 0.590862. Our y1 plus our d1 dz times the iteration and then I can go all the way down. And then for y2 is equal to, it's very similar. We go y2 plus the second derivative times the step. And we can and this can go all the way down. Again, I'll update here in a moment. Then for Y3, we're going, and then for these, we'll just go all the way down. So if we go towards the bottom, these are very high numbers, obviously not correct because we want to get these towards 0. So we're going to use our solver here to try to help better clear this up. So we're going to quantify this by y1 at z, and then y2 at z, not 72, y2 at z. We're going to use this So this will actually just be our y1, which is G1002, and then our h will just be H1002 for our y1 and 2, and then I want sum squared. These two numbers, so we get 1.49679. So now we can, so our objective here, move this down here. Our objective here will be at N5, and we can, where our minimum will be, we're going to be solving for the minimum, and then we're going to be solving for N1 and N2, or more fluxes, will be our changing variables here. And now we can solve. So wait for that to load for a second. No, press. Okay, so we get 2.59 e to the 8. So let's check at the bottom here. And again, much closer to 0 than what we previously had. So, you guys remember what our initial guess was? We guessed about 1 over, I believe it was about 700. So 1 over 700, oops. So 0.1429, which in retrospect, this is not that bad of a guess. It's about 0.001 or 0.0003 off, which in retrospect is pretty good. So our initial guess, where we kind of just went off of like the base pressure, the R10, we were taking some very loose liberties there, and we were still able to generate a pretty good guess. So it just kind of shows you that you can use kind of a decent guess of using our values from part 1. So thank you very much for tuning in, and see you next time.